couple of things to keep in mind about these isometric versus isotonic contractions is that you can have a purely isometric contraction, right? You can have purely isometric contractions. And again, just to remind you, this is where you're trying to lift the load, but it's too heavy. You cannot overcome this load. Your muscles are not generating enough force to overcome this load, right? And you can have a purely isometric contraction. But purely isotonic contractions are rare. They do not usually happen. What does that mean? That means that when you try to lift the load, right? And let's say you do successfully lift that load, which is an isotonic contraction, there was a brief period before you were successfully able to lift that load where your muscle was contracting isometrically. Okay, I'll say that in a different way. Isometric contractions usually precede isotonic contractions. So it's very rare to have a purely isotonic contraction. If you try to lift a 50-pound dumbbell and it's kind of heavy for you to lift, your muscles are going to contract isometrically at first, and then when you generate enough force to lift it, it'll start contracting isotonically and you'll be able to move it. Okay? Now the load is generally not constant, and this just means that when you're carrying, so let's say I'm carrying this bottle, right? Same load, it's the same weight. The amount of force that it's going to take for my muscles to overcome this bottle is going to differ. So the load is going to differ depending on the position of my limb. Right? If I'm carrying this bottle way out here, it's going to appear more heavier. My muscle's going to need more force to lift it. If I'm carrying it close to my chest, again, it's going to appear lighter. My muscle's going to need to generate less force to overcome it. So depending on the position of the limbs, right, that will determine what the load is for that muscle. Okay, so now we've talked about a twitch. We've talked about the two different types of twitch. What we're going to spend most of the rest of the session talking about is factors that affect how much force a muscle can generate. Okay, there are several factors such as the length of the muscle, the width of the muscle, the length of the neurons, right, the motor units that determine how much force a muscle generates. Okay, the first thing we're going to look at is the number of active cross-bridge cycles. Now, I want you to bear in mind, the more cross-bridge cycles you have, the more force you will generate. Okay? So anytime you have bigger muscles, they're generating more force. Why? Because they have more cross-bridges. The second factor is the number of fibers that are contracting. Okay, the number of fibers that are contracting. Let's say I'm lifting this piece of paper, right? I'm lifting this piece of paper. Now, I'm using my biceps muscle, but I'm not using all the fibers of my biceps muscle, okay? Because this is not very heavy. You don't contract your entire bicep muscle to lift a piece of paper, although you are using that muscle group. If I'm lifting something a little bit heavier, I'm going to recruit, or I'm going to call on more muscle fibers to help me overcome a greater load. So the number of fibers that is contracting to overcome that load is going to determine how much force is generated. Okay? Another thing that's going to determine the force is the frequency of the stimulation. All right? The frequency of the stimulation. How fast are action potentials being fired onto that muscle? Right? How quickly after each other are we getting stimulation? Now, this frequency of stimulation is going to be increased action potentials being fired to that muscle. And that can cause, right, an increase in the contraction in two ways. The first one is called TREP, right? TREP. And TREP is basically where we have individual muscle twitches or individual muscle contractions here that are followed one after the other, okay? But they successively generate more tension until they get to this plateau where they're generating as much tension as they can. Okay, I'll say that again. So TREP is where a muscle is being stimulated, right, at such a frequency that the twitches are following one after the other, but they're successively getting stronger. They're generating more force or more tension, okay? But I want you to bear in mind that these are still individual twitches, okay? What does that mean? That means that the muscle is going to contract and then fully relax. It's going to contract again, this time generating a little bit more force, but it will fully relax in between. So these are still individual twitches, okay, and that is TREP. All right, the next way that a muscle can generate more frequency is called summation. Summation, and to understand what summation is, we'll talk about why summation happens. So an action potential takes about 2 milliseconds, right? Very brief, very rapid. Whereas a twitch is going to last anywhere from 10 to 100 to 150 milliseconds. Okay, so this is an action potential here, a couple of milliseconds, and this is the length of time it takes to complete one twitch. Now, as we can see, in the time it takes to finish this twitch, we can generate several other action potentials here. So we can fire an action potential, we can fire another action potential, we can fire another action potential long before this twitch has completed. And this is the basis of summation, right? These twitches will begin to sum, they'll begin to ride onto each other. And this is called summation, okay? I'll say that again. So summation happens because an action potential, which stimulates muscle, is very brief, whereas the time it takes to complete one twitch is much longer. So we can generate several action potentials before this muscle can relax fully again. Okay? All right, so this is a single twitch, and this is what's happening with summation. So we have this first twitch, right? We stimulate it again. The second twitch is going to ride on the shoulders of that first twitch, right? What does that mean? That means that this muscle will not fully relax in between those two twitches. Okay, with TREP, they did. They fully relaxed in between the twitches. With summation, they're adding up, right? They're building on top. Okay, and they're going to successively generate more force as we stimulate another action potential, and so on. All right, and that is summation. Now, if we speed up the amount of action potentials even further, we're going to produce what is called tetanus, okay, tetanus. Now, tetanus is where we have these twitches fusing together, okay? So they're gonna continue riding on each other and becoming so tightly related that they're almost indistinguishable. So we have incomplete tetanus, which is unfused, and that just means that this muscle relaxes a little bit in between these twitches. And we have complete tetanus, which is completely fused. Okay, so we don't have any relaxation at all in between these stimuli. So we stimulate the muscle, we stimulate it again, we stimulate it again, we stimulate it again, and it doesn't have time to relax, right? What's important for muscle relaxation? What needs to happen for muscle to relax? What's that one thing we said needs to happen? Good. Calcium has to leave the cytoplasm, has to leave the cytosol, and that's going to take some time. So if we fire another action potential before all that calcium has left, we're just going to continue adding and adding and building more cross bridges without that muscle fully relaxing. Okay. All right, so the cause of summation and tetanus is the amount of tension developed, right? And this depends on the amount of calcium that is bound to troponin. So if we have lots of calcium in the cytoplasm, okay, and that calcium has not had an opportunity to leave the cytoplasm, we're going to continue having cross-bridge cycling. We're going to continue have those twitches that are riding on each other. Okay. Now, eventually that fused tetanus that we saw, that very last one, this happens when all the cross-bridge cycles are maxed out. We cannot have any more cross-bridge cycling. We're at maximum here, okay? So even if there's more calcium coming in, there's nothing else we can do. We are maximizing cross-bridge cycling. Okay, and this is where the muscle reaches its maximum tetanic contraction. Maximum tetanic contraction is when a muscle is generating the most force that it physically can. Okay, all the cross-bridge cycles are maxed out. All right, so we're going to talk about some other factors that affect force generation. And that's going to be the fiber diameter, right? Now, this is something that's sort of intuitive. A bigger muscle is going to generate more force. Why? Because it has a bigger diameter. So the fiber diameter is wider. And what does that allow for? You have more myofibrils inside. And because you have more myofibrils, you have more cross bridges. Okay, and as we said earlier, more cross bridges equals more force. Okay, so the force generating capacity depends on the number of cross bridges. Okay, so a wider fiber diameter has more myofibrils in it, which has more cross bridges happening. Now, more sarcomeres in parallel is going to equal more force. So that's that same phenomenon. You're going to have more sarcomeres if you have a wider diameter. All right. What's important to know here, though, is that you cannot add thin or thick filaments. The number of thin and thick filaments is constant. So that's not variable, right? A sarcomere has a set number of thin and thick filaments. So you can't add or vary the amount of thin and thick filaments. What you can do is add more sarcomeres, okay? And that's what happens in bigger muscles. Okay, next there's the fiber length, right? And this one is pretty important. The fiber length. So the length of the fiber at the onset of the contraction affects how much force is being generated. Question?
Yeah, about the addition of sarcomeres.
Mm-hmm.
So does that happen through like replication of myofibrils, or is it muscle cells? How do you get these?
So the muscle can get bigger and generate more myofibrils, which have those sarcomeres on it, right? But you can't add to a single sarcomere. You cannot add thin and thick filaments. Yeah, that's the take-home point. So it's easy to think because you say, okay, more cross-bridge cycling. Let's add some more actin and myosin to this sarcomere. You can't do that. That is constant. What you can do, right, in bulking up that muscle is add more myofibrils, which has more sarcomeres, right? What is also constant is the number of fibers. So you can make those fibers bigger. That's what you do when you work out. You can make them bigger, and they're going to have more sarcomeres in parallel, but you cannot add myofibers, and you cannot add thin or thick filaments to the sarcomere. Okay, any questions on that? All right, so the next thing we're going to talk about is the fiber length, and that is the position of the sarcomere when the muscle is contracting. And it needs to be at an optimal length. What does that mean? An optimal length means that the muscle needs to be at its resting length in order to generate the maximum amount of tension that it can. Okay? So if you have a muscle that is already stretched or relaxed, it's not going to generate as much tension as it can because the actin and myosin, right, the thin and thick filament are just not close enough in contact. Okay? So when you have cross-bridge cycling, you're not going to have the maximum amount of overlap that you can. I'll say that again. The muscle needs to be in an optimal length so that you can have the maximum amount of overlap, the maximum amount of thin filaments sliding past thick filaments to generate as much force. If you have that muscle stretched, right? And you do have cross-bridge cycling, you're gonna have a very minimal amount of overlap here. We want more overlap. Again, if you have that muscle that is too short, it's way shortened, you're not gonna have as much overlap because it's just too contracted, okay? And in C2, the muscles are at their optimum length. And that means that in your body, the way it is, because your muscles are attached to two bones, they're at their optimal length, okay? Those two bones are holding them nice and taut so that they're at the optimal length that is needed to generate maximum force. Okay, so let's explain this a little bit further here, okay? Let's take a scenario where you had the muscle greater than optimal length, right? Greater than optimal length, okay? Which is what this looks like here, right? Greater than optimal length. The actin, so remember this is actin, or your thin filament. This is myosin, or your thick filament. And they're so far away that if you do engage cross-bridge cycling here, probably just the first few myosin heads will overlap with actin. You will not have maximum overlap here, okay? The muscle is greater than its optimal length. All right, let's take another scenario, the opposite. Let's say you have a muscle that is less than its optimal length, okay? The myosin heads are almost touching the Z line, right? It's way too shortened. This is not the optimal place to start cross-bridge cycling. Okay, when these begin to move, remember they're supposed to move towards the Z line, there's not very far that they can go. So they're not gonna generate as much force as if they were a bit more relaxed. Okay, and that's what we mean by optimal length. It needs to be at that perfect length to have the maximum overlap when it does contract. Okay, so if we look at the center here, we can see this is a nice, comfortable length. That's your optimal length. So when you do have cross-bridge cycling, you have the maximum interaction between actin and myosin, and you generate the most force that you can for that muscle. Okay. All right, any questions so far? Any questions so far? All right, so what we're going to talk about now is recruitment. And we kind of started talking about this a while ago, but recruitment is where you call on more muscle fibers to increase the amount of force that is produced with that muscle. So in my scenario that I mentioned earlier, I talked about lifting a paper, right, versus lifting a bottle or a weight, okay? So lifting this paper, I'm not gonna need very many muscle fibers to be contracting. But as the load gets heavier, I wanna recruit a few more fibers, okay? And that is what recruitment is. Calling on more muscle fibers to generate more force to help that muscle lift its load, okay? Now it's important to understand that more muscle fibers increases the force, but what we're recruiting is the motor unit. Remember we said a motor unit is made of the motor neuron and all the fibers it is innervating, okay? So if I'm recruiting more muscle fibers, I'm not gonna recruit one fiber. I'm gonna recruit another motor unit. And that motor unit may be innervating, say, 5 fibers. So in me recruiting that extra motor unit, I'm actually recruiting 5 fibers. Okay, so it's not a single fiber by fiber, but it's by the entire motor unit that we recruit. All right, let's look at this scenario here. So we have motor unit X and motor unit Y. Motor unit X is innervating 5 fibers, or has 5 fibers in it. Motor unit Y has 7 fibers. All right, we can see on the graph below that when motor unit X is engaged or contracting, right, it's generating an okay amount of force, right? Not very much. Okay? An okay amount of force or tension. Motor unit Y is generating a little bit more force or tension, not significantly more. But if we recruit both of these units together, they're both actively generating force. We are going to sum the amount of force that is being generated. Okay? So if motor unit X was contracting to overcome a load, we recruit motor unit Y, we would significantly increase the amount of tension that was being produced to overcome that load. And that's why recruitment happens.